Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Zeeman effect and its types and explanation towards normal Zeeman effect and anomalous Zeeman effect in terms of quantum mechanics. Let's begin. What is Zeeman effect? Zeeman, a scientist, first discovered the splitting of energy levels of an atom in a constant external electric field. In an constant external electric field, the energy levels of an atom is splitted. That effect is known as Zeeman effect, and it is of two types. One is normal Zeeman effect and another one is anomalous Zeeman effect. What is normal Zeeman effect? Again, the splitting occurs, but the atoms having spin 0, means the splitting of energy level exhibited by atoms having spin 0 is called normal Zeeman effect. And in case of anomalous Zeeman effect, there will be some spin, means the splitting of energy levels exhibit by atoms having non-zero spin is called anomalous Zeeman effect. Zeeman effect and its types: normal Zeeman effect and anomalous Zeeman effect. Let us discuss the explanation towards the normal Zeeman effect and anomalous Zeeman effect in terms of quantum mechanics by using the vector atom model. First, quantum mechanical explanation of normal Zeeman effect. According to quantum theory, a polyelectronic atom, means more than one electrons, is known as polyelectronic atoms, possesses an orbital angular momentum L vector. Orbital angular momentum that is L vector, and orbital magnetic moment that is mu L vector, and the gyromagnetic ratio is given as, use the gyromagnetic ratio of this polyelectronic atoms. The gyromagnetic ratio is given as, that is the ratio of magnitude of mu L to that of magnitude of L, and which is equal to E by 2m. Charge of electron, this is the mass of electron, where E stands for charge of an electron, and m stands for mass of an electron. Means the vector mu L is directed opposite to that of L vector. Just in a figure, we have already discussed in case of vector atom model, but just overlook it. That is the nucleus of an atom, and electrons are revolving around that of nucleus. Here is the electron is revolving around that of nucleus. That one is the L vector, and mu L vector is just opposite to that of L vector, that is the mu L vector. okay, as electron is regarding charged and current direction opposite to that of electron flow. When atom is placed in an external magnetic field, we apply an external magnetic field B here, external magnetic field, say along that of z direction, that is the z direction, and the angular momentum L vector precedes around that of B vector, that L vector precedes around that of B vector with the quantized components, and that quantized components is known as the Z component, that is Z component of L, Lz given as ml h cross, where ml is the orbital magnetic quantum number, where ml is the orbital angular quantum number, and that value of ml from the limit plus L to minus L, and there are total number of allowed values 2L plus 1 allowed values, and that precision is known as Larmor precision, and in presence of that magnetic field each L level is split into 2L plus 1 levels. So, just a important point I write, this is the Larmor precision, that precision is known as, this precision is known as Larmor precision, Larmor precision. We have already discussed in case of vector atom model. In that of external field, the orbital angular momentum precedes around that of external field, and that type of precision is known as Larmor precision. In that of Larmor precision, what happened? Since it has 12 plus 1 allowed values, it indicates in precision in the presence of magnetic field. What I write? In the presence of magnetic field, in the presence of magnetic field, each L level is split into what? 2L plus 1 levels. And each is characterized by the value of ml. So, according to that of Larmor precision or Larmor theorem, the angular velocity of precision is given as omega is equal to, that is the ratio of mu L divided by L into B, that is E B divided by 2m, that is the angular velocity of that of Larmor precision. And the intersection energy, since due to the applied of that of external magnetic field, the energy levels are split. Due to that of splitting, the intersection energy level is caused due to that of precision, and that intersection energy of such a precision, the intersection energy of such a precision is the product of angular velocity and projection of L vector along what? Along the field. Along the field means along that z direction. The field is along z direction, that is del E is equal to angular velocity omega and z component Lz, that is known as omega z component, that is L cos theta. So omega is equal to E B divided by 2m L cos theta, that is the z component, that is ml h cross, ml into h cross. This is the intersection energy. Now in terms of wave number, the intersection energy will be in terms of wave number. What we have? Wave number means 1 by lambda, that is nu bar, that is the wave number, is equal to del E divided by SC. How we get that one? As we know, del E is equal to h nu, Planck's constant, into frequency, and in place of frequency we write that is c by lambda. Therefore nu 1 by lambda is equal to del E by SC. So del E, the value of del B is put here, that is E B divided by 2m HC ml h cross, and that quantity, or we say the wave number nu bar, is equal to L naught into ml, where L naught is equal to E B h cross divided by 2m SC, which is in terms of Planck's constant, h is equal to h by 2 pi, h is cancel out, it will be E B divided by 4 pi mc, which is known as Lorentz unit. Okay, this is the descriptive way, or the quantitatively we discussed normal Zeeman effect. Now taking an example to explain how the transitions are carried away. So example, let me consider the transition of 1 d2 to 1 p1. The transition from 1 d2 to 1 p1, these terms corresponds to, here L is equal to, in that of case L is equal to what? S P D 0 1 2, that is L is equal to 2, here L is equal to 1, that means the transition from L is equal to 2 to L is equal to 1. And the breaking, that level is breaks into, the allowed values is 12 plus 1, the allowed values is 12 plus 1, means 2 into 2 plus 1 means 5, it is splits into 5 levels, and here 12 plus 1 will be 2 into 1 plus 1, that is 3. That level split into 5 that split into 3, and the values of ml, here the values of ml are stands from 2, 1, 0, -1, -2, 5 allowed values. Here ml stands for 3 values, that is -1, 0, 1, and the transitions are carried out by using a selection rule, and that selection rule is through which the allowed transitions are possible. The selection rule is del ml is equal to 0 plus -1. The transitions which obey the selection rule, that is the allowed transitions. Let us draw that of transition. The transition from 1d2 to 1p1. Let me draw the lines. That line is at 1d2 line, and that line let we prefer 1p1 line without field, without magnetic field. When no field is applied, the transition, the allowed transition from 1d2 to 1p1 be that one. Means here no field is applied, here no field is applied, we get one single line here, one single line here. After applying an external constant magnetic field, what happens? That line split off into 5 spectral lines, that is split off into 5 lines. 1, 2, 3, 4, 5. These are the spectral lines. These are the spectral lines when we apply an external magnetic field. The splitting looks like this, that is 0, 1, 2, -1. Let I choose here upper half is plus, that is +1, +2, here is -1 and -2. Okay, these are for ml. Now 1p1, 3 levels, that is 0, here +1, here -1. Now the transitions, the allowed transitions are 0, +1 and -1, means the change in del ml. First we consider -1. Let we consider -1. -1 in the sense, in that of line, what should be the transitions? The transitions are when we stands for 0 to 1, 0 to 1, it will be -1, -1, we get -2 to -1, -2 to -1, -2 to -1, there will be -1, then -1 to 0, -1 to 0, it will be -1, then 0 to 1, then 0 to 1, it will be 0 to 1, that is not 0 to 1. Okay. Next, allowed values is 0. 0 means 1 to 1, 0 to 0. 0 means what? 0 to 0. 0 to 0. Minus 1 to minus 1. Minus 1 to minus 1. Plus 1 to plus 1. Plus 1 to plus 1. Plus 1 to plus 1. Next, plus 1. Plus 1 in the sense 2 to 1. 2 to 1. Then 1 to 0. 1 to 0. Then 0 to minus 1. 0 to minus 1. The result will be plus 1. These are the allowed transitions. So that means when we apply the field, when we apply that field, the lines are formed. Here one line, that is line, that line, 3 lines are formed, and these lines are known as sigma lines, and that line is known as pi lines. Pi lines are formed when the field direction is same as that is parallel to that of field direction, and in that of case sigma lines that is perpendicular to that of field direction, means the magnetic field is perpendicular. This is the happenings in a normal Zeeman effect. This is the happening in normal Zeeman effect. This is an example of normal Zeeman effect. What we studied here, the quantum explanation of normal Zeeman effect, and this is the example towards that of normal Zeeman effect. Now the explanation towards anomalous Zeeman effect. Now explanation of anomalous Zeeman effect. Again same concept. When an electron revolves around that of nucleus, it executes an orbital angular momentum, and due to that of own spin, the spin angular momentum is created inside that of electron, that is the orbital angular momentum, and due to spin we create spin angular momentum, and the resultant of these two creates the total angular momentum. And when we applied an external magnetic field along that of z direction, when we apply the external magnetic field along that of z direction, the precession takes place. The precession L precedes about that of j, S precedes about that of j, finally the precession of z takes place. Okay, all these things are studied in case of vector atom model. So here we have to explain anomalous Zeeman effect in terms of vector atom model. How to explain? We know the ratio of mu L, orbital magnetic moment, to that of orbital angular momentum is equal to E by 2m. E is the charge of electron, m is the mass of electron, which is known as gyromagnetic ratio, and the ratio of spin magnetic moment mu s to spin angular momentum magnitude of s is equal to 2e divided by 2m, and due to the inequality total magnetic moment, total magnetic moment mu is equal to, that is mu L plus mu S is not exactly antiparallel to J, that is not exactly antiparallel to total angular momentum J. Since J is invariant, since J is invariant in the sense it indicates that, so L vector, S vector, mu L vector, mu S vector and mu are precise around J. Precise around J. Due to that of precision, so we have mu of J, mu of J mu of J, the ratio of mu of J to that of J is equal to E by 2m into G, E by 2m into G, where G is known as Land's G factor, Land's G factor, and here the value of that Land's G factor is 1 plus J whole into J plus 1 plus S whole into S plus 1 minus L whole into L plus 1 divided by 2J J plus 1 under root, that is the Land's G factor. Here from Larmor's theorem, the angular velocity of precision, the angular velocity of that precision of J, the precision of J around B, is given as what? Omega is the angular velocity, that is mu J divided by magnitude of J into B is equal to mu J by J, that is E by 2m into G, that is E G by 2m into B, and the energy of precision is the product of what? The frequency and the projection of J along B. In that of case also we get the intersection energy will be that much in normal Zeeman effect. Same thing happened here. The energy of precision or intersection energy, the energy of precision, that is del E is equal to, that is the product of angular velocity and the projection of J along B, that is JZ, that is EG divided by 2m, ZJ means mj h cross b, mj h cross b. And in terms of wave number, in terms of wave number, 1 by lambda is equal to nu bar del E divided by SC, del E is equal to Eg divided by 2 mch mj h cross b is equal to g mj eb. In place of h cross we substitute h by 2 pi, 4 pi mc, or nu dash is equal to g mj. That term is known as L naught, which is known as, that term is known as Lorentz unit. We studied in normal Zeeman effect case. The Lorentz unit means the product of G and mg to that of Lorentz unit. Now we practically see, taking an example, how the transitions are carried out, how the transitions are carried out. So we have to understand that anomalous Zeeman effect mathematically. Taking an example, consider the splitting of sodium atom. The sodium D lines, means D1 and D2 are the two lines are formed. The transitions takes place 2 p half to 2 s half. Another transitions 2 p 3 by 2 to 2 s half. Two transitions are taken into considerations for that of sodium atom. Now look here, you have to take what are the terms L, S, J, and number of Zeeman levels, means 2j plus 1 allowed values, Landage G factor, and mj shift in Lorentz unit. Okay, just take another page. What are the terms L, S, J, number of Zeeman level, is 2j plus 1, that is G, Landage G factor, and mj, the allowed values from plus j to minus j, shift in Lorentz unit, So first we take 2s half, s will be, since s that is 0, the spin is half, j, that one is the j is half, number of allowed value, that is 2j plus 1, that is 2, Landage G factor, that is 2. We put the values in that of equation of Landage G factor equation. So putting this, we get that tabulation results 2, or for our convenient we know the Landes G factor as 2. Then the allowed values be plus minus half, since J is equal to half. The Lorentz shift we calculate here, the Lorentz shift as calculated here, GMG into L naught. So the Lorentz shift is here is 1, therefore 2s1. Then for 2p half L 1 S spin half J half, number of Zeeman levels that is 2, Landes G factor will be 2 by 3, that is plus minus half, Lorentz shift be plus minus 1 by 3. Another one, two p 3 by 2, next transition, next term 2p 3 by 2, 2p 3 by 2. So L is equal to 1 S half 3 by 2, that is 4 by 3, here is plus minus 3 by 2 and plus minus half, then shift plus minus 2 and plus minus 2 by 3. Now using this table we can take the allowed transitions. We introduce the selection rule. Here the selection rule be del mj is equal to 0 and plus minus 1, and there will be no such transition from 0 to 0 level. There will be no such transition from 0 to 0 level. Like took that of transitions, how the transitions takes place. Here 2p 3 by 2 to what 2p half, last one, that is 2s half. Two lines are created, means first transition from 2p half to 2s half, 2p half to 2s half, that is the D1 line. Then 2p 3 by 2 to 2s half, 3 by 2 to 2s half, that is D2 line. Now the allowed transitions, this field is created when there will be no such external magnetic field, but when we apply an external magnetic field, what happens? The splitting takes place of that of spectral lines. So what are the splitting takes place? So in case of 2p 3 by 2, the allowed values are 2p 3 by 2, the number of 2p 3 by 2, the number of allowed levels are 4 number of splittings. So the splittings are 1 2 3 4 number of splittings. That is what? Plus minus 3 by 2 to plus minus half, that is minus half minus 3 by 2, it will be plus half plus 3 by 2. Then 2p half, 2 number of splittings, 2 splittings, one is minus half and another one is plus half. Then for 2s half, that is also 2, plus half minus half. Okay. Now according to the selection rule, the transitions are plus minus 1 0 0 1 minus 1. So the for first line, for D1 line, what is the transitions? The transitions are from minus half to plus half, minus half to plus half, then half to half, half to half, then minus half to minus half, minus half to minus half, then half to minus half, half to minus half, half to minus half. These are the allowed transitions for D1 lines. Next, the allowed transitions for D2 lines. What are the allowed transitions? Then minus half to half, minus half to half, minus half to half, minus 3 by 2 to minus half, minus 3 by 2 to minus half, minus 3 by 2 to minus half, then plus half to plus half, plus half to plus half means 1, sorry 0, that is plus half to plus half to plus half to plus half. Plus half to plus here is the plus half to minus half na, plus half to minus half. The transitions are plus half to minus half, the transitions. Okay. Minus half to minus half, minus half to minus half, minus half to minus half, minus half to minus half. Here plus half to plus half means that is the transition line, plus half to plus half. Okay. Next, 3 by 2 to minus half, 3 by 2 to minus half, 3 by 2 to minus half. Next, minus half to plus half, minus half to plus half. Okay, completed. Minus 3 by 2 to minus 3 by 2 to minus half, minus 3 by 2 minus half, completed. 1 2 3 4 5, one transition, one transition, one transition, 1 2 plus half line, one transition will be there, that is plus half to minus half, plus half to minus half, and plus half to plus half. Plus half to plus half. Okay. These lines are formed due to the apply of external magnetic field. There are 4 lines, there are 6 lines. In that of case, the 4 lines are formed. This is pi, that is sigma. 2 pi lines, 2 sigma lines, and here 6 lines has 2 pi lines and 4 sigma lines. 4 sigma lines are formed due to the application of that external magnetic field. So, this is the example of sodium lines D1 and D2. So, with the help of this video lecture, we understand what is Zeeman effect. Two types of Zeeman effect, one is normal Zeeman effect, another one is anomalous Zeeman effect, and the quantum mechanical explanation of normal Zeeman effect. And the example of that normal Zeeman effect, how the spectral lines are formed. Next, explanation of anomalous Zeeman effect, and the examples of that of sodium lines, how the transitions are took place according to the selection rule. These are the transitions. So, with this useful and informative notes, let me wind up this session. Thank you.